How's it going, everybody? In this video, we're going to take a look at BGP a little bit more in depth than our high-level overview that we just did. The concept of BGP that most people don't grasp is the idea of the autonomous system number. Now, we talked about this in EIGRP, where all routers in the same autonomous system will share the same routing information. The minute you leave your autonomous system and you go to a different one, in order to get routes from one autonomous system into another one, you have to redistribute. Well, that's not quite the same way that BGP works. When you have an autonomous system, you're either given one or you can allocate yourself one depending on how they work out. Now, an autonomous system is, per Wikipedia, is a set of routers under a single technical administration. So they use an IGP and common metrics to determine how the traffic will route within the AS, and use an inter-AS routing protocol to determine how traffic leaves the network. So basically what that's saying is you're going to use an IGP like OSPF, EIGRP inside your network to determine how traffic gets from point A to point B inside your autonomous system, and then when it wants to leave, to go to the internet or to another site that you might have that's remote, that might either use public internet, some sort of VPN that might be using public internet to get reachability to a remote site, or an MPLS type of solution. Either way you look at it, it's going to be leaving your domain. There's a small chance it might be using BGP, not all the time, but in case your environment runs BGP, this is going to be the breakdown for it. Now, I just mentioned you might be able to assign yourself an autonomous system number. Now, normally this is not going to happen, especially if you have an assignment through IANA or the Internet Assigned Numbers Authority. You go out to IANA, you go out to them and say, this is just a joke, but you go out there and beg to them on your hands and knees, I'd like an autonomous system number. But you don't really do that. You fill out some paperwork and you say, you go through, it goes to a registrar. The registrar looks at what's going on and will allocate you a autonomous system number. Once you have that autonomous system number, that is yours and yours alone. Nobody else can use it. Now, you'll hear me talk about some other things as we go along that you can do later on that will, like for instance, during path selection and filtering, you can actually screw up the internet if you don't know what you're doing, especially if you're on the edge in the BGP domain. You can screw up the internet. People think, well, how do you screw up the internet? It's very, very easy to screw up the internet. You can simply tweak something the wrong way and you can throw everything into a hiatus. So we'll take a look at that as we go along here, but the idea behind your autonomous system number is that when you use it, you're going to be using it to peer with somebody else. So you have your autonomous system number and you want to peer with the provider or another company that's got a different autonomous system number. You can peer with them. Now, there's when you peer with the provider is usually going to advertise you a bunch of internet routes. You know, whether it's the full table or just a small select group of routes that you might need. You might be signaling to them you want these routes, or you might have just the default route being advertised, and you would just send everything to them and then let them take care of the routing. And there's a question: what small subset of routes would you be pulling in? Typically, the ones that I see the most are going to be the ones where you have a larger company and you've got several sites throughout the world, and you know their public IP address space. So you can actually go out there for BGP and you can have them routed via BGP, and you can say you want to advertise, you want them to advertise routes into BGP per their subnet, so you have reachability to them. And you can actually create like VPN rules and some other capabilities that are inside applicable to your environment that would allow you to only receive updates from them. So you could filter things out. I'm not going to go to that level. I mean, that's more of an advanced level that you could use. But for instance, like let's say you're running DMVPN, which we'll be talking about here very soon as soon as we get done with BGP. You can be running DMVPN and have it set up to where you know all of the public address space that all of your company's networks have allocated, and you can have it set up to where only those address spaces will be listening for DMVPN connections as well as IPsec connections. So if anybody else out there happens to try to ping you and they realize you're running DMVPN on the back end for some reason, it will prevent them from trying to form a DMVPN connection with you. So that's just one way. It's basically it's I guess it kind of in a way I guess you could say it's like ASA, where you can turn off the ping capability to where the ASA doesn't show up in the trace route, or you can turn off ICMP on the outside interface to where the box will not respond to pings if you were to ping the public IP. So it's a way for you to minimize minimize your attack surface from the public facing side. So that's just one of those situations. Now, the way that the autonomous systems are broken down is you have two different variables. The first variable is a 2-byte autonomous system number. The 2-byte autonomous system number is what was originally assigned in BGP version 4, and not for IPv4, but BGP version 4. There's 3 versions of BGP before that. The BGP that we're going to be working with is going to be version 4 and has been around as long as I can remember. And I've been working with BGP for about 4 years now. So the values that you're going to get are 0 through 65535, and 0 and 65535 are not assignable as far as I'm aware. So you can only assign BGP 1 through 65534, I believe is what it is. I'll have to look at the actual syntax, but I don't believe you can assign 0. And then you have the public assignments are 1 through 64511, which gives you 64,511 autonomous systems that you can go out there and assign to customers. Well, seems kind of limiting, don't you? Don't you think? 64,000? Well, I'm pretty confident there's more than 64,000 companies running BGP. Well, the powers that be, which I have nothing to do with, like the IETF and IANA and things like that, the people that actually make all the protocols and get everything running, thought to themselves, well, that's kind of a limited version, and we'll talk about the 4-byte autonomous system here in a moment. So the private autonomous system range is 64,512 through 65535. Now, that range right there is 1,023, 24, however you want to cut the mustard, 1,024 addresses. These are the ones you can choose to assign to yourself if you choose to do so. Now, if you have a public IP or public autonomous system number, you can go in there and assign that, and then you can run on the back end. You can do things like confederations and run your public range inside of that. I'm not going to get too deep into when you would use a private autonomous system number, other than the fact that you can run it and then peer with the provider. They will peer with you. Well, depending on the provider's peering rules, they may not peer with you because you're a private AS number. There's some things in there, some tweaks you can actually do to remove private AS, and it would actually advertise up. I don't remember the details of that one because I've only just looked at it once or twice, but you can actually remove your autonomous system number and have, I believe the provider will advertise their number on your behalf. I believe is how it works. So we'll take a look at that more in detail when we get to it, but not something I typically worry about. Now, when you get into the details, the 4-byte field, currently there is a 4-byte field. So RFC 19 or 4893 support for the 4 octet AS number space, and if you're running Cisco code, 12.4.2014 and above supports this. Now, what is a 4-byte ASN? Well, essentially a 4-byte ASN is going to be, you're going to take the original 16-byte ASN, or I'm sorry, 2-byte 16-bit ASN, and you're going to tack on an additional 16 bits. So look at an IPv4 address and take that number and go 1 to the power of 132, and what does that give you? 4.2 billion or something like that. Almost 4.3 billion. Well, what that basically means is there's that many autonomous systems out there now. I don't quite think there's 4 billion companies that are running BGP. There could be. There might be one day, but as far as I know, there's not right now. Maybe a couple 100,000 at the most. And the idea behind this here is to allow you to scale BGP to the much larger setups that it needs nowadays. And the key thing to remember here is when you're dealing with BGP, you have to understand where people are coming from when they're working with BGP. and that's the one thing we're going to get into as we go along here. Most people don't grasp how this stuff really works. So as we go through, we'll break down exactly what that means in regards to getting things situated. So if you happen to have a router running older 12.4 code or older, and it happens to pair with a router that's running 12.4/24T or newer, and that particular router happens to be running 4-byte ASNs, the way that you would get that to work, or the way you would be able to tell that, is the AS number would be encoded as 23456, and you would be able to do an AS path dot notation, and basically that would let you see what it's actually running. We'll take a look at exactly how that would work and go from there. So it's not very complicated to get BGP operational. It's actually pretty straightforward. Establishing BGP peers is pretty simple as well. Like IGP, the first step is to find neighbors to exchange information with. However, BGP does not have its own transport, so you need to either have a route to the next hop, or you need to be directly connected to them. So the thing here is that since it doesn't have its own transport, it has different types of neighbors. So neighbors are not discovered by default, and they do not have to be directly connected. Again, that means is if they are directly connected, then you know they're on the same wire as you. Well, not necessarily the same wire. In our case, they are physically connected to each other. But in the real world, there might be a couple different connections to getting them to where they need to be. But at the end of the day, they have layer 3 reachability. That's the main point. So when you're dealing with that, now this technically is not 100% true anymore. This was written a while ago. This is like a year or two old documentation. But this is back before, and I'm not even sure when the feature was enabled in BGP, but you can actually form BGP neighborships dynamically using the listen command. And I will show you what that looks like. The listen command is actually very, very simple to use, and I actually use it in a lot of environments where I run BGP over DMVPN, because it makes that capability scale better, because it's going to be a pain in the butt for every time you want to join a spoke to the hub to type that command in and get everything operational. You just have to make sure you have access to the spoke, and then configure it to talk to the hub, and the hub is already going to have that dynamic information inside of it, and be able to form the adjacency rather quickly. So those are just some of the capabilities you can use. But again, it depends on the situation you're running into. That may or may not be the best solution. So from a transport perspective, we're going to break down how this all works. Uses TCP port 179 for transport. It implies that it needs an IGP to work inside your internal network. So if you want to run eBGP and iBGP at the same time on your edge, and then have internal routers running iBGP, if you want that to be the case, then they need to have reachability to each other, because by default, a iBGP neighbor does not send updates that it learns externally inbound. So we'll talk about that more when we get to iBGP issues, but we'll talk more about that in detail later. But basically what you're going to be doing is you're going to be saying the neighbor statement tells the process to listen for remote addresses via TCP port 179. Initiate a session to remote address via TCP port 179. If a collision, higher router ID becomes TCP client. So the idea here is if you're sending and receiving TCP messages from you and another router, and they're both port 179, that's going to be a clear indication that's BGP. And if you guys send and receive at the exact same time and things go boom, then whoever, in order to determine who's going to do what, you have to, because both of you could be sent to the server or the client. It doesn't make a difference. But like I said, in a collision, the higher router ID dictates who the client's going to be. Now, if they're the same router ID, then actually what will end up happening at that point is the session will be reset, because it doesn't know what to do. So typically you're going to set one of you is probably going to have a higher router ID, simply for the fact that if you don't configure a loopback address with a dedicated loopback for a router ID, then whatever IP address is configured that's the highest numerical value on any up-up interface, that's going to become the router ID. And then usually what's going to end up happening at that point is two people are going to have two routers are going to have two different IP addresses, and then from there, that's how it's going to break that's going to be the tiebreaker. Now, from a transport perspective, you can determine who the server is. TCP server must agree on the client session, where the client session is coming from. If the server does not expect a session, it will refuse it. This is where they come into play, where when you send any message outbound, it's going to be sourced off of the interface closest to the destination. Now, with BGP, you can change that, and if the destination is not expecting the source to be coming from where it's coming from, it'll say, nope, that doesn't pass, I'm going to drop it. You'd use the update source command to accomplish this. So we'll take a look at that more in detail when we get into iBGP and eBGP. So if you're running on non-service provider trains, like the S train, the M, or if you're on like the M train or the T train, you can type in a command that says show control plane host open ports. And I did this on a router just to see what it would look like. And I did actually on my router here at home. I did that, and it says active internet connection server established. I had an active telnet connection to it at the time, and I also had a UDP port because it's my home router happens to be my DHCP server. So that's situated. So now let's take a look at real quick at the BGP states, and that we'll break that down, and then we're going to get into the peering types. And that'll be the next video, because it's going to be a breakdown as to how we go through and get everything situated. Now, the idea behind this isn't very complicated, but if you've never dealt with this before, it can be kind of intimidating. So the BGP states, you have idle. The initial state that the BGP routing process enters when the routing process is enabled or when the device is ready, reset. So the device waits for a start event. So after the device receives a TCP connection request from a remote peer, the device initiates another start event to wait for a timer before starting a TCP connection to a remote peer. If the device is reset, the peer is reset, and the BGP routing process returns to the idle start or idle state. What does that mean? That means if you are you're going to have the active and the idle. Active and idle. Active and idle. So you turn the engine on, but the car isn't in drive yet. So you're sitting in park. The minute you press the brake and you put it into drive, you are now in the active state. You're going to wait for a dedicated timer to time out, which I believe is 30 seconds. A minute. A minute's scan timer. So you're going to wait that minute, and if nothing happens in that minute, you're going to then put it back in park. You're going to wait a back-off time, and you're going to put the car back in drive. So the idea behind this is you're going to be consistently trying to form a peering, trying to talk to each other. So it's going to be like if two OSPF routers are trying to form an adjacency with each other. You're going to send you're going to multicast out, and you're going to multicast out from the other guy. If you guys both hear each other, you can form an adjacency. And then you have to agree. You have to get to the, what state is that? That is the init state. The init state is where you go in, you are sending a hello, and you're receiving a hello, and the receiving hello is going to have the sender's router ID in the reception. So the idea here is you're waiting for somebody to call back and say, yep, I can talk to you. Now, the way that this breaks down with the connect is the BGP routing process detects that there's a peer trying to establish a session with the local BGP speaker. And that's what BGP routers are called, BGP speakers. The active process, the active state I should say, is the BGP routing process tries to establish a peering the session with a peer device using the connection retry timer. Start events are ignored while the BGP process is in the active state. So if the BGP routing process is reconfigured or if any error occurs, the BGP process will release system resources and return to the idle state. So those three right there are going to be, if you are having a problem peering, if you're seeing any one of those, if you do a show IP BGP summary and you see idle or active, and you don't see anything happening where the neighbor relationship comes up, Or if you're doing a debug IP BGP and you don't see open sent, open receive, or established happening, then you have a three-way handshake issue. Because remember, BGP is a TCP application. In order for you to peer, you have to have TCP reachability. That could mean that either you and the connection between you and the peer have a layer 3 issue, where TCP cannot be sent back and forth. You have a filter in place where you're dropping or not sending TCP port, port 179. You could be dropping BGP traffic. There could be on the wrong VLAN if you're in between two different. If you're on a switch, you could have 2 ports in the wrong VLAN. Again, at that point, there's not a whole lot of issues that can be in play between you and the other guy. Now, that's not 100% true, because I have heard of MSS issues and stuff like that causing problems with updates and resetting neighbors. I've not personally seen that, but I've heard of people that I've worked with that have ran into that problem. Especially, I worked with one guy for a while, and he saw that a lot in India. He was working in India. He was doing an ISP connection to India's largest ISP, which we'll just, for lack of a better term, IndiaNet, if you will. I don't honestly know what they are, if that's it or not. But he was trying to connect to IndiaNet, and there was an MSS issue. The MSS maximum segment size was set wrong on his side. Now, open send. The TCP connection is established, so you and the neighbor can talk to each other via TCP. The BGP routing process sends an open message to the remote peer and transitions to the open sent state. The BGP process can receive other open messages in the state. If the connection fails, the route process will go back to the active state. So open sent, you guys are talking. Things are working, ports are open, life is good. Typically at this point, if anything happens, it's usually a MTU issue, is what I've seen. Open receive receives the open message from the remote peer and waits for an initial keep alive message from the remote peer. When a keep alive message is received, the BGP routing process transitions to the established state. So until you see that keep alive, you don't do nothing, man. And the funny thing about it is, and if you were to watch the debugs on this, and we'll see what it looks like here in the next video when we actually go to connect, it can be a little convoluted, if you ask me, on how things like that would get set up, because it's like, okay. Doesn't always make sense in the debug messages, and I've even done Wireshark captures. It doesn't make 100% sense, but at the end of the day, as long as the TCP peering comes up and stays up, you're good. Then we have the established state. This means that everything else prior to this has worked, and now you have formed a BGP peering. At this point is when you would see the syslog message come up, as long as you've got console logging turned on. You would see the BGP adjacency is up, and you would see the router ID of the remote peer pop up. BGP adjacency up, yada yada yada. Things would look good. And then if you were to do a show IP BGP summary, you wouldn't see a state. So it would be a word in the prefix received. It would be a 0. There wouldn't be any. If you see active, idle, open sent, open received, established, if you see anything like that, then it hasn't gone full adjacency yet. Adjacency does not mean forwarding. It can, but not necessarily. So if you form a peering, you can form a control plane peering, but not actually send anything in the data plane. And that's the idea behind how BGP path selection peering forms. It's relatively straightforward. So the session reset. For those of you that do not want to lose your jobs, or do what I've heard referred to as a resume generating event, a hard reset. What a hard reset is you are dropping the TCP sessions completely and rebuilding them. If you do this, you completely drop everything. So BGP resets, all the BGP neighbors go down, the routes you learn go away, and reconvergence has to happen. Now, in our environment that we're going to be testing this in, BGP converges pretty quick, and path selection doesn't take very long. But if you work for a company that's got a big router with a couple of connections for BGP, is receiving the full internet routing table from 2 different views. We'll talk about views here coming up later on. It could take 10-15 minutes for network connectivity to come back up. not 30, 40 seconds like it will be in our environment. So if you do a clear IP BGP star and you don't have a maintenance window configured or set up, and you have active traffic going on, you might as well take your badge and turn it into your manager and start looking for work, because you just basically took down the network. And it's never a good sign when that happens. So the hard reset is only good if it's a last-ditch effort to try to get something to work. That's if the soft reset and the dynamic inbound soft reset doesn't work, or what we like to refer to as the route refresh capability. The soft reset is when you do a clear IP BGP soft. This does not break the TCP peering. All it does is it triggers an update out and says, hey man, this is what I got. And it's a way for you to send a routing update. It's a triggered update. It's a user configured triggered update. And this is what I highly recommend in a production environment. And I'm going to raise my voice here and reiterate. Do not, under any circumstances, unless you have prior authorization to, do a hard reset. I will show you what it does, just so you guys are aware of this, because I'm assuming you don't know BGP. But this will break your network if you do a hard reset. It's okay in a lab, but if you do it in production, unless you got the okay from the boss, and he understands the impact, don't do it. Do a soft reset, which is a clear IP BGP soft, clear IP BGP star soft, or clear BGP BPMV4, or whatever the case might be. In our case, it's going to be clear IP BGP star soft. Now we have dynamic inbound soft reset. What that basically does is you can choose if you want to send and receive an update, just send an update, or just receive an update. And you're going to be sending out and saying, hey buddy, I need an update, and your neighbor's going to send you what it's got. So this is good because BGP updates don't happen like IGP updates do. They don't just happen. Sometimes it takes 10, maybe 15 minutes in production, a couple minutes in a lab sometimes, for all of your updates to come in. You make a routing change, a routing update, path selection issue, whatever the case might be. You do something to BGP in your environment, and you don't. It's not going to propagate right away. I mean, it's not an instantaneous thing. BGP is extremely slow in production, so it's one of my favorite protocols in the lab and in real life. But if you don't know what you're doing with it, you make a change, and you're like me, and you're pretty good on the command line, and you jump over to another box, and you're doing a check. Usually, I use my speed to test things, and I'll say, okay, this is just to prove to you that this route has not propagated yet. I'll do it, like, oh, it's not there. I do a clear IP BGP star in, and that's going to be able to get me what I need to go where. Now, if you do a soft, okay, clear IP BGP star soft, that's an outbound and an inbound at the same time. Soft is a, hey buddy, here's what I know, as well as can you send me what you know. Now an inbound soft is where you do a clear IP BGP star in or star out, depending on how you want to do it. Star in is going to affect the way the traffic is going to be coming towards you, and star out is going to be the way the traffic leaves you. So it's pretty straightforward when you think about it, but that's the general idea of how this stuff pans out. So now I've gone over the way the BGP works and some of the details to it. In the next video, we'll actually look at our peering and get some stuff situated. And there's a question, where am I going to be doing my BGP? Well, what I'm going to do is, in our environment here, we're going to have two ISP routers, BGP 6 and BGP 13. These are both ISPs. We're going to be peering 3 and 5 to 6 and 13, as well as 7. And then we're going to be peering over here. So right now we have OSPF running over this frame relay connection and EIGRP running over this one. I'm going to remove OSPF and EIGRP from the frame relay environments. I'm going to peer BGP between these guys. And this is going to simulate a remote site that you would have BGP reachability to. And this is going to, I'm also going to turn this router right here, which is it's actually a 3725 router. I'm also going to turn him into a BGP speaker. So he's going to be an ISP as well. Same thing with this guy over here. And the reason for that is so when we get into our peering, we have to peer with an ISP. So we're going to have an intermediary connection. So it's going to go us, local service provider, remote site. And that's going to show you guys what it looks like to actually get routes in between. And we're going to see exactly how that pans out. It's not super complicated to grab, but if you don't understand what the general consensus and idea of it is, that can cause you problems. So we'll see exactly how that would break down as we go along here and go from there. So I hope this has been informative for you. I'd like to thank you for viewing.